Hello everyone and welcome to my new YouTube channel. I'm thrilled to have you here as we explore one of the most fascinating topics in electric engineering, dynamics of electric drives and four-quadrant operation. Whether you are a student, a professional or just someone curious about how electric drives work, this video is for you. By the end of this 20-minute session, you will have a solid understanding of how electric drives operate, their dynamics and the importance of four-quadrant operation. Let us start with the basics. What are electric drives? Simply put, electric drives are systems that control the motion of electric motors. They are the backbone of modern automation and are used in a wide range of applications. From industrial machines and robotics to electric vehicles and even household appliances like washing machines and fans. An electric drive system typically consists of three main components: the electric motor, the power converter, and the controller. The electric motor, which converts electrical energy into mechanical energy, and the power converter controls the supply of power to the motor. The controller, which decides how the motor should operate based on the desired speed, torque, and direction. Now, why is this important? Well, without electric drives, we wouldn't be able to control the speed, torque, or direction of motors effectively. Imagine driving a car without an accelerator or brakes. It would be chaotic. Electric drives bring precision and control to motor operations. Now that we know what electric drives are, let's talk about their dynamics. The term dynamics refers to how the drive responds to changes in load, speed, and torque. Think of it like when you press the accelerator in your car, the car speeds up, and when you brake it slows down. Similarly, in electric drives, the motor's speed and torque change based on the load and control signals. These changes don't happen instantly. There is a transient response, a brief period where the system adjusts to the new conditions. For example, if you suddenly increase the load on a motor, it will take some time for the motor to adjust its speed and torque to match the new demand. Understanding this dynamics is crucial because it helps engineers design better control systems that ensure smooth and efficient operation. Let us break down this further. The dynamics of electric drives are governed by two keys: mechanical drive and electrical dynamics. Mechanical dynamics involves the motor inertia, friction, and the loads it's driving, whereas electrical dynamics involves the motor's electrical characteristics such as inductance and resistance and how they interact with the power supply. For example, in an electric vehicle, when you press the accelerator, the motor needs to deliver more torque to overcome the vehicle's inertia and friction. The electrical dynamics ensure that the motor draws the right amount of current to produce that torque, while the mechanical dynamics determine how quickly the vehicle accelerates. Let's move on to one of the most fascinating aspects of electric drives, four-quadrant operation. This concept is all about how a motor can operate in four different modes depending on the direction of rotation and the direction of torque. Let us break it down quadrant by quadrant. The first quadrant, which is called as forward motoring. Here, the motor rotates in the forward direction and the torque is also in the forward direction. This is the most common mode, like when your car is moving forward on a road, on a flat road. The motor is consuming electrical energy and it is converting it into mechanical energy to drive the load. Second quadrant. In this mode, second quadrant is also called as forward braking and regenerative braking. In this mode, the motor is still rotating forward, but the torque is reversed. This is like regenerative braking in an electric vehicle, where the motor acts as a generator to slow down the car and recharge the battery. Here, the motor is converting mechanical energy back into electrical energy. Third quadrant, which is called as reverse motoring. In this mode, both the rotation and torque are reversed. This is like driving your car in reverse. The motor is again consuming electrical energy to produce mechanical energy, but in the opposite direction. Fourth quadrant, that is reverse braking. Finally, in this mode, the motor rotates in reverse, but the torque is in the forward direction. This might seem a bit counterintuitive, but it's useful in certain applications like cranes where you need to lower a load slowly. Here the motor is again acting as a generator, converting mechanical energy into electrical energy. Understanding four-quadrant operation is crucial because it allows us to design systems that can operate efficiently in all possible scenarios. For example, in electric vehicles, regenerative braking helps recover energy that would otherwise be lost as heat, improving the overall efficiency of the vehicle. Now that we understand the four quadrants, let us look at some real-world applications. The real-world applications are electric vehicles. As mentioned earlier, electric vehicles use four-quadrant operation for acceleration, first quadrant, and regenerative braking, that is second quadrant. This is not only improves efficiency but also extends the vehicle's range by recovering energy during braking. Cranes use four-quadrant operation to lift and lower heavy loads smoothly. When lifting a load, the motor operates in the first quadrant. When lowering the load, it operates in the fourth quadrant, ensuring controlled and safe movement. Elevators use four-quadrant operation to control the speed and direction of the cabin, ensuring a smooth and comfortable ride for passengers. Fourth is the wind turbines. The generators operates in different quadrants depending on the wind speed and direction, allowing for efficient energy conversion. The most important, the most important part of this dynamics of electric drives and four quadrant operation is not just academic, but it's practical. It helps engineers design more efficient systems, reduce energy consumptions, and improve the performance of machines. Whether you are working as an electric on an electric vehicle, a robotic arm, or a wind turbine, these concepts are fundamental. For example, in industrial automations, precise control of motor speed and torque is essential for maintaining product quality and reducing waste. In renewable energy systems, energy efficient operation of generators can significantly improve energy output, and in electric vehicles, regenerative braking can extend the vehicle's range and reduce the need for frequent charging. And that's a wrap up on today's topic. I hope I hope you enjoyed this deep dive into dynamics of electrical drives and four quadrant operation. If you found this video helpful, don't forget to like, share and subscribe. Thanks for watching. We'll see you in the next video.